Today we are going to talk about the polymer mechanical properties. So, under this we are first going to talk about the stress strain relationship of polymer, because this is different, distinctly different from what I have earlier told you about the stress strain relationship in metals or ceramics. This is different for polymers. So, we have to see that, and also we have to see how we can develop various mechanical models for the polymers. So, various mechanical models we will discuss. So, these are also known as the parameter models, okay, for the polymers. And then we will see the stress strain behavior. So, first we will see the stress strain relationship, okay, how we can mathematically express the stress strain relationship, and then we will talk about the stress strain behavior. So, stress strain behavior is what we will see once we develop the mechanical models, and then we will talk about fracture and fatigue, and finally we will talk about the factors that affect the mechanical behavior of a polymer. Now, the first point is that what is the stress strain relationship of a polymer and how is it different from the stress strain relationship that we know, for example, for the metals. Now, for the metals, for the simplest case, if it is a a single stress and a single strain, that means if you are not about a kind of a three-dimensional representation and a tensorial representation of stress and strain, for a single stress and strain, the relationship is sigma equals to E epsilon. So, which means that stress is directly proportional to the strain. However, for the polymer it is not like that. There are time anomalies in polymer, that means not all the stress you will be able to find out at a particular instant. The stresses will be changing with respect to the time, and that is also true for the strain. So, the generalized relationship, we call it as a generalized Hooke's law, is something like this that we have shown here, which is also known as a generalized Hooke's law, that the stress along with its derivatives, first order, second order till the nth order derivative of the stress. So, that is in the left hand side, and in the right hand side you have strain along with its derivatives. So, you see the simplest case of the metal can also be represented by the generalized Hooke's law, provided you put A1 to AN equals to 0 and B1 to BM equals to 0. So, then what you will get is that A0 sigma equals to B0 epsilon, or sigma equals to B0 over A0 epsilon. So, which is something like E epsilon, where E is B0 over A0. So, that is why you can say that the simplest case of the stress being proportional to strain is actually a special case of this generalized Hooke's law. Now, this generalized Hooke's law we can also write in a little more compact manner as the A0 sigma separately and then rest of the terms. Similarly, B0 epsilon separately and then rest of the terms. If all these coefficients A0 to AN and B0 to BM are constant, then the material is linear viscoelastic material. There is no guarantee that always they will remain constant, these parameters will not vary with time, but for certain polymers we call it standard linear solids, where these parameters would remain constant. Now, there are many models, that is what these are the mechanical models that have been developed in terms of representing various types of polymeric behaviors. So, the first model is the Kelvin-Voigt model. As you can see, in a Kelvin-Voigt model you have a spring and a damper. So, this is a spring and a damper and they are working in parallel. So, for the spring you know that stress is proportional to strain. So, you can write that if sigma is supposed the stress in the spring. So, sigma 1 in this case in the spring and epsilon 1 is the strain in the spring. Then if the elastic constant is E, which is nothing but the elastic modulus, then sigma 1 equals to E epsilon 1. And similarly, for a linear viscous dashpot, the stress here is proportional to strain rate. So, if sigma 2 is the stress here and epsilon 2 is the strain here, then sigma 2 is not proportional to epsilon 2, but it is proportional to the strain rate. So, that is sigma 2 equals to eta times d epsilon 2 dt. Now, if I am applying a load that is generating a stress sigma and an epsilon strain in the material, then this force is actually getting divided into partly in the spring and partly in the the dashpot, right. So, you can say that with a suitable area constant sigma equals to sigma 1 plus sigma 2, essentially since the sigma is working on the same area, it is something like sigma times A equals to sigma 1, that is implicit that the A will get cancelled, times A plus sigma 2 times A, and since the A gets cancelled, so you get this relationship that the sigma stress is sigma 1 plus sigma 2, and strain wise the total strain is the same as the strain in the spring or as the strain in the dashpot, because both of them are the same integral part of the same material. So, you are going to look at only one strain, there will be two strains in it. So, hence epsilon equals to epsilon 1 equals to epsilon 2. So, now if I apply this relationship that sigma equals to sigma 1 plus sigma 2. So, sigma 1 is nothing but your E epsilon 1 and sigma 2 is nothing but your eta d epsilon t dt, and epsilon 1 equals to epsilon 2, then you are going to get sigma equals to E epsilon plus eta d epsilon dt, because there is only one epsilon, since epsilon 1 equals to epsilon 2 and that equals to let us say epsilon. So, this is what will be the relationship. Now, what is our generalized relationship? That is A0 sigma. So, generalized relationship I can write for two terms, that is A0 sigma plus A1 d sigma dt equals to B0 epsilon plus B1 d epsilon dt. Now, let us look at it, because here anyway you have up to first order variations. So, we can say that there is a sigma term in this equation, that means A0 is there and A0 equals to unity. There is no d sigma dt term, so you can write A1 equals to 0. There is a B0 term because of this E part, so that means B0 equals to E, and there is a second constant B1 which is eta here. So, that is what is B1 equals to eta. So, that means for the Kelvin-Voigt model, it is a special case of the generalized Hooke's law, where A0 is 1, A1 is 0, and needless to say that A2 onwards all the other terms are 0, and B0 is E, B1 is eta, needless to say B2 onwards all the terms are 0. So, that is what is a special case of a generalized Hooke's law, which is the Kelvin-Voigt model. Now, Kelvin-Voigt model is signified by parallel combination of spring and dashpot. So, can there be a series combination? Yes. If you take a series combination, then we will call that model to be Maxwell model. Now, in this case, it is the same force which is passing through the spring and then to the dashpot. So, essentially here the relationship is just the reverse here, that is the stress is same, sigma equals to sigma 1 equals to sigma 2, and the strain here however is partly due to the spring and partly due to the dashpot. So, it is epsilon 1 plus epsilon 2. So, if I take the derivative of the first equation, then I get d epsilon dt is d epsilon 1 dt plus d epsilon 2 dt. So, this is actually taking derivative of strain with respect to time equation 1, and this is equation 2. Okay. So, you get equation 3 by actually derivating equation 1. Now, if you substitute the values in the right hand side, that means your d epsilon t dt is d epsilon 1 dt, and what is your epsilon 1? That is your relationship that sigma 1 equals to E epsilon 1. That means your d epsilon 1 dt is nothing but your 1 over E, because d sigma 1 dt we can write from the spring is actually E d epsilon 1 dt. So, d epsilon 1 dt is nothing but 1 by E d sigma 1 dt, right. So, that is your d epsilon 1 dt, and that is nothing but 1 by E d sigma dt, because sigma 1 equals to sigma. Similarly, if you look at this part of the relationship, you can write directly that d epsilon t dt is nothing but 1 over eta sigma 2. So, if you add these two together, you are getting this relationship where d epsilon dt is actually 1 over E d sigma dt plus sigma over eta. Now, if you take this relationship and compare it with the standard, generalized Hooke's law, you will see that in this model A0 is 1 by eta, A0 is 1 by eta, A1 is 1 over E, and then A2 onwards it's 0, B0 is 0, B1 is 1, and B2 onwards are 0. So, that is what is our Maxwell model as a special case of the generalized Hooke's law. Can there be more complicated models? Yes. You can have more complicated models like one parameter model, which is linear elastic spring. So, these are like simple one parameter models, but from here you can actually come to the two parameter models, which I have just now explained. So, these are two parameter models, and then you can have 3 and more parameter models. Now, the one parameter model spring denotes actually perfectly elastic behavior, and the dashpot behaves perfectly viscous behavior. So, Maxwell model, where the spring and dashpot are in series, they actually predict the fluid like behavior, and they do not describe the recovery part of it. On the other hand, in the Kelvin-Voigt model, they predict more solid like behavior, and they do not prescribe the stress relaxation. So, that is the typicality of the two parameter models. More than that, if you go to 3 parameter model, then you will get two models. One is called a standard linear solid model. In the standard linear solid model, if you look at it, that there is a spring and a damper which are in parallel, and also there is a spring and a damper which are in series. So, that is the relationship that you get for a standard linear solid model. That means, if I try to see this in terms of A0, it is 1, A2, A1 is eta over E2, A2 onwards it is 0. And if I look at B0, this is E1, and B2 is eta times E1 plus E2 by E2, and this is B1. So, this is B1, and B2 onwards it is actually 0. Now, let us look at the standard linear fluid model. For that model, unlike in this case where you have two springs in parallel, here you are going to get two dampers in parallel and a spring damper combination in series. So, for this case, if you work on, you will get this one to be the stress strain relationship. Again, here you can write A0 as unity, A1 as eta 2 over E, no other parameters are there, A2 onwards in the 0 with respect to stress. With respect to strain, B0 is 0, B1 is coming out to be eta 1 plus eta 2, and B2 is eta 1 eta 2 over E, and rest of the terms are 0. So, that is the again another special case of a generalized Stokes law. Now, let us look into the viscoelastic deformation, that how the viscoelastic deformation can be modeled as something which is clearly in between the elastic and the viscous behavior. Suppose I take a material and then I apply a load which is like a step load, as has been shown in this case. That means at time Ta I have applied the load, and then at time Tr I am unloading the load. Now, if it is an elastic material, as soon as you apply the load, that means as soon as there will be stress, you will see instantaneously strain will be developed without any loss of time. And then as soon as you remove the load, if it is within the elastic limit, you will see that the strain will disappear as well. Can a viscoelastic material or can a polymer behave in this way? No. Why it cannot behave in this way? It is because inside the polymer there are many chains, and since there are many such chains, each chain has its own dynamics and they are going to interfere with each other. So, as a result, it will never be an instantaneous process of strain development. Rather, you will see that the polymer is taking some time to develop the strain, and once again the load is removed, the strain will once again disappear from the system. So, a polymer is essentially, if it is totally viscous, it will take time to develop the strain, okay, and beyond the point of Tr, that strain will remain in the system. But in the case of a polymer, it will be addition of the two behavior. That means as you apply the stress or the load, you are going to get some instantaneous strain development. So, this is the part which is related to, we call the glassy modulus part. So, this is instantaneous, and then gradually you will see that the it is deforming more. So, it is just like the viscous behavior, and there you are going to get an additional term which is the loss modulus, which will come into picture. So, both glassy modulus and loss modulus, sometimes this is also known as storage modulus, will come into picture in this instant, and then once you are unloading, you are going to see that it is actually the strain is coming down. So, an amorphous polymer may behave like a glassy polymer at low temperatures where it is instantaneous. That is why it is actually called glassy modulus. A rubbery solid at intermediate temperature where it is partly you are getting elastic behavior and partly viscous behavior, and this happens above Tg, that is the rubbery phase. And then a viscous liquid, if the temperature is further raised, it will become a viscous liquid where it will behave totally like a viscous behavior. So, for all intermediate temperature, the polymer is a rubbery solid which shows the viscoelastic behavior, which is a combination of this elastic and the viscous behavior. Now, if you look at the stress strain behavior, you know that there is the brittle behavior. Some polymers which are highly actually crystalline, they show this kind of a brittle behavior, and then there are these elastomers which are like rubber, which does not really does not have a high strength, but before it fails it takes a very high strain. That is what is like the elastomers typicality, and there could be polymers which are between the two. That means it behaves initially like a brittle polymer and then it behaves like an elastomer up to a certain point, maybe some 4%. This is strain in percentage, so maybe up to 4%, 5% strain, and then you will suddenly see that the failure has occurred in the system. If you compare it in terms of modulus of elasticity, the polymer's modulus of elasticity is from MPa to just GPa range, something like up to 4 GPa. If you compare that with metals, it is something like 50 to 400 GPa. So, as far as the elastic modulus goes, metals are far ahead of the polymers. If you look at the tensile strengths also, the polymers can take tensile strength up to 100 MPa, but that is the fracture point of the polymer, and for the metals it is from 100 to about 1000 MPa. So, clearly speaking, the polymer beats the metal beats the polymer both in terms of modulus of elasticity and tensile strength. But the point where polymer beats the metal is this elongation capability, because before failure polymers can take up to 1000% of its original length kind of deformation, whereas metals fail by a strain which is less than 100%. So, what it means is that polymers are compliant, they try to adjust with the system, they are more adaptive and they deform a lot before the final failure takes place. On the other hand, metals do not deform that much in comparison to the polymers, so they fail much earlier, less than 100%. But also I told you earlier that ceramics are even weaker than metals in terms of these, that they fail even before, they cannot take any high strain at all. So, with a very low strain you will see a sudden failure in the ceramics. Now, this brings us to the discussion on the fracture in polymers. So, one point is that polymers have a low fracture strength compared to metals and ceramics. That's because its strength itself is low, and the fracture mode differs from polymers to polymer. For thermosetting polymer, the fracture mode is like brittle material, which is thermosets are highly cross-linked, you remember, and for the thermoplastic polymer, both brittle as well as ductile failures are possible. In such polymers, crack forms at region of localized stress, and there will be stress concentration in scratches, notches, sharp flaws, etc. The factors that will favor the brittle fracture are temperature reduction, increase in strain rate, sharp notch presence, increased specimen thickness, and polymer structure modification, for example by raising the Tg of the polymer, that is the glass transition temperature of the polymer. As you can see here, that if a polymer is brittle, then it something like melamine or phenolics, then it behave in this manner. If it is elastomer type, soft and flexible like polyethylene PTFE, then it behaves in this manner, and if it is in between, then it is tough and ductile. ABS nylons are of this category, which actually takes a much higher stress level and also much higher strain level in comparison to the two extremes. The fracture mechanism in polymers, there are 2-3 important points in it. One is that there is this amorphous thermoplastics, where for below Tg they are actually brittle. So, it has a low fracture resistance, it behaves like a glassy material, I already told you. Above Tg they are ductile, so it gives you higher fracture resistance, and there will be always a plastic yielding prior to the fracture. Now, the fracture phenomenon that you will see often in such a material is called crazing. Crazes are what? These are the region of localized plastic deformations, and they will form at highly stressed regions associated with the scratches, flaws and molecular inhomogeneities. they will lead to the formation of small and interconnected microvoids, and then the region between microvoids you will see the fibrillar bridges. Under load the fibrillar bridges will elongate and break, microvoids will grow and merge, thus the crack propagation will happen with respect to the applied tensile stress in the polymer. Let us look into a simple example to see that how this crazing will occur in a polymer. So, here I have taken a small sample of a normal plastic bag cutting, that is a low density polyethylene, and this low density polyethylene I am subjected it to tensile stress. So, suppose your bag is very heavily loaded, this bag, you will also notice the same phenomena. So, here I am actually trying to stress it. Now, initially you can see that it has all uniform yellow color. What will happen if I apply little bit of stress in it? So, I am applying the stress. As you can see that there are some spots and some lines, straight lines which are getting created. These are actually the last attempts of the polymeric chains to orient itself towards the direction of stress. If I apply more stress, you will see that there are more crazing lines, so that means more polymers are aligning, and there are some white patches you will see where actually the color changes are happening and the microvoids are about to start. Now, if I pull it further, and you can see that there is a sudden failure, and you can see that this sudden failure has happened where this color change has happened, and there will be formation of such small micro holes. This is one such micro hole. So, the failure could have either happened from the left or from the right side. Now, it is just a chance where the stress concentration is suddenly maximum, the failure will take place there. So, you can see the color change, you can see the crazing, and you can see this formation of the micro holes. So, that is typically a kind of a fracture mechanism that you will see in the polymers. Now, when a polymer is subjected to cyclic loading, then the fatigue comes into picture, okay, because there are many aircraft structures etc., where there are polymeric wings, and hence there will be always a cyclic loading that will be associated with the system as the plane takes off and land. So, under cyclic loading, however, the behavior of the polymer is pretty bad in comparison to the metals. So, they are more sensitive to loading frequency than for metals. High frequencies and or relatively large stresses can actually cause localized heating, and that would soften the material and leading it to failure. Now, here I just want to tell you one thing, that frequency and temperature are actually two just kind of a you can exchange one with the other by keeping in mind that if the temperature increases, then what happens? Suppose I am drawing the modulus of elasticity of a polymer. Initially it is in the glassy phase, then the transition rubbery phase, and then it comes to the glass transition happens in the rubbery phase, and then the flow occurs. With respect to the frequency, just the reverse will happen. That means the low temperature is actually similar to high frequency behavior. So, if there is a high frequency excitation of a system, then the polymer will behave like it behaves in low temperature. That means it will behave as if it is in the glassy region. That means under high frequency excitation, the polymer will be very brittle, and under low frequency it is somewhat similar to the high temperature behavior. So, this is the low frequency behavior, and that is in the rubbery phase, and this is your glass transition phase. So, low frequency, why do we get a rubbery phase? Because the polymers get more time to adjust itself, the chains get more time to adjust. So it behaves like a rubbery material, and the low frequency is exactly similar as the high temperature behavior in the polymers. So number of cycles to failure, if you look at it, for example PTFE number of cycles to failure, you can see that it can be anywhere, it's starting from 10 cube to 10 to the power 7. Similarly polyethylene, and the stress amplitude, however, it fails at a very low stress amplitude level PTFE, and the high stress amplitude something like PET can take or polystyrene can take high stress amplitudes. So that is the fatigue behavior of the polymers. So what are the factors that affect the mechanical properties in polymers? Number one is of course temperature. Increase in temperature can produce decrease in elastic modulus, I have already shown you. It can also create reduction in tensile strength, enhancement of ductility, and reducing the strain rate also produces the same effects in the polymer. So as you can see here that PMMA, for example, at a low temperature 4 degrees centigrade it behaves like a brittle material, and at 50 degrees centigrade you will see that it behaves like a rubbery material, 60 degree even so. In between is the phase where the glass transition occurs in the system. So that is how sensitive a polymer is to temperature. The second important point is the molecular weight, because for many polymers tensile and impact strength increases with increasing the molecular weight, and this is due to increased chain entanglements. Larger is the chain, more is the chance of entanglement, and hence the strength tensile and impact strength increases. Also the viscosity increases. The third point is the degree of crystallinity. Higher the crystallinity, higher the close packing. So higher density would mean more strength, higher resistance to both dissolution and softening by heating. So that is the role of degree of crystallinity in the polymer. Finally, the fourth point is the cold drawing, which is analogous to strain hardening in metals, is used in the production of fibers and films. Molecular chains become highly oriented. In fact, that's why I was showing you that as you are drawing, you will see that these kind of parallel chains were appearing in the system. That is what is the cold drawing. And the properties of the drawn material are actually anisotropic. Perpendicular to the chain alignment direction, the strength is reduced. So that is why you will see that in the perpendicular direction, in this direction it is weaker, and in this direction it is stronger. And that's why when the cracks occur, you will see that the cracks are occurring and failing in the weaker direction for cold drawing in a linear polymer. So this is where we will put an end to the mechanical models of polymers. In the next lecture, we will talk about composites now and the classification of the composites. Thank you.